Okay, thank you.
Okay, so next presenter is Simona. Jenny.
Right. Yeah, I hope it works. I'm Simona Bekeraitė, and I'm here today to talk about Python and astrophysics. But I think there's an issue with with my slides.
I'm really sorry about that.
Well, in the worst case, we can do it like this. Maybe it's me. So I've been doing a PhD in astrophysics for the last few years, and my work is centered at distribution functions of rotating galaxies, 3D spectroscopy, fundamental properties of galaxies in the universe, their comparison with simulations, and relations with dark matter that the galaxies contain. That's a picture I've done a few years ago, so it actually depicts the perceptions of people what astrophysicists do. So we don't do horoscopes, and we don't do rocket science, we don't do magic, and we don't watch through a telescope. Most of the time, the only thing we are doing is writing really lousy Python code. And why is that? The reasons are twofold. First of all, astrophysicists were in big data before big data was cool, so we were getting lots of data from the observatories since the 80s or 90s, and that's a bad picture of big data. I collect them. The second thing is that we usually get little or no formal training in scientific programming, and this has changed just recently. So most of the scientists still don't use version control. We keep our data in large CSV files instead of databases, and we have really a hard time to start using programming efficiently because we are just thrown into it and we have to deal with that. So one of the outputs of this is that people tend to acquire skills which are more and more needed in industry, like all the big data tools and so on. And then people leave astrophysics. So that's a problem, one of them. Historically, these are the main programming languages in astrophysics. So C is mostly used for fast numerical simulations, where, for example, we start a simulation of the universe, start with some first principles, and just grow the universe and see how it evolves. Otherwise, C is used anywhere where efficiency is needed. Fortran has lots of excellent scientific libraries, so we use it for, I don't use it anymore, but people use it because it has a large source base. R is quite seldom in astrophysics, although some people do use it, and a language which has been very popular was IDL, which stands for Interactive Data Language. I think it was specific to astrophysics, as far as I know. It was closed source, very expensive, proprietary. You needed a license to share your code with someone else, but it had some good array manipulation tools, so therefore it was quite popular a while ago. And now there has been a broad movement to Python, which is mostly to Python 2 so far, because we don't want to update our code. We just want to run it, see what happens, and go on looking at our galaxies and doing science. But there has been also movement towards updating it. I will do a quick run-up through core Python packages in astrophysics. I'll skip some of them which are not specific to Python, which are not specific to astrophysics or which are so popular that I assume most of you know them. So first of all, NumPy, which is the bread of scientific computing. If everything else is butter and caviar, NumPy is the bread. And I like it because it allows to do fast operations on imaging data. For example, you have a large image or n-dimensional image, and you can, here, for example, you can do rejection of outliers. You can efficiently reject bad data points, and you don't have to write a loop to do it all. Otherwise, NumPy allows to do efficient array indexing, so you don't have to write several loops going over an n-dimensional array, which also is prone to errors because we don't have much experience with that. And for example, a thing like this, unrelated project would have taken me, I don't know, several minutes to code, and in NumPy it's just a couple of lines. SciPy is lots of tools which provide the fundamental tools of scientific computing, also engineering, technical computing, and so on. And it has lots of functions for basic mathematical operations, linear algebra, signal processing. It's mostly used either on a per function basis or as a basis of other tools such as Pandas, Scikit, and so on. So Pandas is a newcomer in astrophysics, and it's great for time series analysis. I don't do time series analysis because galaxies rotate, in millions of years, so this library doesn't quite cut it, and neither do our observations. But people who do transient source analysis, like looking for exoplanets, do this a lot. Use it, and it's really useful. For example, if you want to find an average, if you want to smooth your data and see what are the trends in it, it's really easy to use. Scikit-learn is a library which is also widely used in the industry, and it's a machine learning and data mining library. It's also a basis of several specific tools, but if anyone is interested in machine learning in Python, that's the library you have to use. It's used widely in astrophysics as well. And it is a basis of AstroML, which I used quite a lot, and it's a cool module for machine learning and data mining, but it's geared towards astrophysical data sets in a sense that in astrophysics, the data is usually noisy, it's contaminated, it has low signal to noise. Well, it is non-periodically spaced, it has differing error bars, which are usually types of data which are not easy to crack with traditional methods. And this module provides methods to deal with that and really extract the small features in the data which would have been missed otherwise. It's quite advanced. For example, we have this, and at the upper panel we have the observations of a variable star, and at the lower panel we can see the periodogram, the periodicities which could appear in the data. And even from such sparse data, we can estimate the period of variations of the star and get to know about it. I'm sorry, you probably cannot see it. AstroPy is a collection of modules. It's community written, and it provides basic functionality used for astrophysics. It's specific to astrophysics, so it's probably useless to most of you. It basically lets do the things which we would be writing on everyone separately. For example, there is a cosmology subpackage. Cosmology is a branch of astrophysics which investigates the universe as a whole, like its history, development, start, ending, contents, and geometry. And for example, here we say we would like to import lambda CDM from cosmology subpackage, and we create an instance of the universe with these cosmological parameters. Congratulations, there is an instance of the universe. And then we'd like to calculate some quantities which we would need for our observations. For example, we are observing a galaxy at redshift 3. Redshift is a method of looking at distances in the universe, or at look-back time, because when you're observing the universe, you are looking back into time. And this subpackage provides methods to do it, so you can calculate the distance to your galaxy and estimate how bright it really is, for example. The other thing where Python is used widely in astrophysics are cosmological simulations. I mentioned before, these are large simulations which run for long periods of time, and where people try to simulate a universe which is similar to ours or which is different to ours, and see what physical constants and parameters are important, and if we have estimated them correctly. So it's an interface to an simulation, the largest one so far, I think. And this picture shows dark matter, which are these violet strands, and hot gas, which are like very hot gas at the centers of galaxy clusters. So there's a Python interface provided by the simulation collaboration, and it allows to obtain their data. Without it, it would be very difficult to query it, because there is some large data sets. Of course, when you're doing science, there are a lot of specific tasks and a lot of specific solutions which you can find in scientific literature. Here, there's an excerpt from a code I wrote where I needed to model a galaxy's rotation and its position in space and its rotation parameters. So I had to do Bayesian Markov chain Monte Carlo modeling of it, and select the best one, the best parameters. I've been using MC, which is a popular package for Markov chain Monte Carlo simulations written in Python. So you have to look for it, and one has to follow the literature to see what's being done. And that's a takeaway message for me. Now, anyone who wants to do science, it's practically vital to learn to code. I've met people who did their PhD calculations in Excel. I've met people who were painting plots in Microsoft Paint, but well, they are outliers. Don't do it. And that's a brief introduction into Python and science. Thank you.
A fascinating talk, another angle on Python. Any questions? I wonder whether you use that only, you mentioned sort of in the industry thing. Is there a source of industry in Lithuania for astro things, or is it mostly within research community?
I'm not sure I get the question. I mean, astrophysical specifics are like completely inapplicable, but the tools,
I don't know.
we learn to use, I think they are now in big demand, like machine learning tools and so on.
So it's okay. So stupid question, me. Yeah, sorry.
Sorry.
It's pure science then, so basically it's research community, and then within that research community you apply for international grants, participate in international projects, or how does it work currently with astro things in Lithuania?
I'm not studying in Lithuania. I was in Germany, so. But I think the situation is similar.
Okay, so it's pretty good in Germany then.
Astrophysics is very international, so it's same in most places.
So thank you for the answer. Sorry for the stupid question.
It's not stupid. Thanks.